Well, welcome back to our course, Networks and Distributed Systems, based on the textbook by Jim Carouse and Keith Ross, Computer Networking, a top-down approach. We have been studying the network layer, and we are now into lesson number 10. We just finished looking at the IP protocol dealing with addressing. Now we're going to move into lesson 10 and begin the discussion of ICMP. So let's get started. Recall that the network layer of the Internet has three main components. The IP protocol discussed in the last lessons, the Internet routing protocols, which include RIP, OSPF, and BGP, which we'll be discussing later, and ICMP, which we will look at now. ICMP, Internet Control Message Protocol, is used by hosts and routers to communicate network layer information to each other. The typical use of ICMP is for error reporting. For example, when running a telnet, FTP, or HTTP session, you may have encountered an error message such as destination network unreachable. We've all seen that one before, or something similar. This message had its origins in ICMP. At some point, an IP router was unable to find a path to the host specified in your application. That router created and sent a Type 3 ICMP message to your host indicating the error. ICMP is often considered part of IP, but architecturally it lies just above IP, as ICMP messages are carried inside IP datagrams. That is, ICMP messages are carried as IP payload, just as TCP and UDP segments are carried as IP payload. Also, when a host receives an IP datagram with ICMP specified as the upper layer protocol, it demultiplexes the datagram's contents to ICMP, just as it would demultiplex a datagram content to TCMP or UDP. ICMP messages have a type and a code field and contain the header and the first 8 bytes of the IP datagram that caused the ICMP message to be generated in the first place, so that the sender can determine the datagram that caused the error. Selected ICMP types are shown in this slide on your screen. Note that ICMP messages are not just used for signaling error conditions. The ping program sends an ICMP type 8 code 0 message to the specified host. The destination host, seeing the echo request, sends back a type 0 code 0 ICMP echo reply. Most TCP/IP implementations support the ping server directly in the operating system. That is, the server is not a process. Note that the client program needs to be able to instruct the operating system to generate an ICMP message of type 8 code 0. Another interesting ICMP message is the source quench message. This message is seldom used in practice. Its original purpose was to perform congestion control to allow a congested router to send an ICMP source quench message to the host to force that host to reduce its transmission rate. We have seen in the unit on transport layer that TCP has its own congestion control mechanism that operates at the transport layer without the use of network layer feedback such as IMP source quench messages. You remember that we introduced the Traceroute program earlier, which allows us to trace a route from host to any other host in the world. Interestingly, Traceroute is implemented with ICMP messages. To determine the names and addresses of the routers between the source and the destination, Traceroute in the source sends a series of ordinary IP datagrams to the destination. Each of these datagrams carries a UDP segment with an unlikely UDP port number. The first of these datagrams has a time to live of 1, the second of 2, and the third of 3, and so on. The source starts timers for each of the datagrams. When the nth datagram arrives at the nth router observes that the time to live of the datagram has just expired. According to the rules of the IP protocol, the router discards the datagram and sends an ICMP warning message to the source, type 11, code 0. This warning message includes the name of the router and its IP address. When this ICMP message arrives back at the source obtains the round-trip time from the timer and the name and the IP address of the nth router from the ICMP message. How does a traceroute source know when to stop sending UDP segments? Recall that the source increments the time to live field for each datagram it sends. Therefore, one of the datagrams will eventually make it all the way to the destination host. Because this datagram contains a UDP segment with an unlikely port number, the destination host sends a port unreachable ICMP message, type 3, code 3, back to the source. When the source host receives the ICMP message, it knows it does not need to send additional probe packets. The standard traceroute program actually sends sets of 3 packets with the same time to live. Therefore, the traceroute output provides 3 results for each time to live. As you can see, many of the ICMP messages are seeking information about another host. Ping, you can consider saying, "Are you there?" And traceroute is asking for directions from the router to router to router. For this reason, and I've done this myself, an administrator may include instructions in the router's access control list to ignore these messages. In the early 1990s, the Internet Engineering Task Force began an effort to develop a successor to the IPv4 protocol. The prime motivation for this effort was the realization that the 32-bit IP address space was beginning to be used up. With all the new subnets and IP nodes being attached to the Internet being allocated unique IP addresses at a breathtaking rate. To respond to this need for a large IP address space, a new IP protocol, IPv6, was developed. The designers of IPv6 also took this opportunity to tweak and augment other aspects of IPv4 based upon the accumulated operational experience with IPv4. The point in time when IPv4 addresses would be completely allocated was the subject of considerable debate. The estimates of the 2 leaders of the Internet Engineering Task Force's Address Lifetime Expectation Working Group were that addresses would become exhausted in 2008 and 2018, respectively. In February of 2011, IANA allocated out the last remaining pool of unassigned IPv4 addresses to a regional registry. While these registries still have available IPv4 addresses within their pool, once these addresses are exhausted, there are no more available address blocks that can be allocated from the central pool. Although the mid-1990s estimates of IPv4 address depletion suggested a considerable amount of time might be left until IP address space was exhausted, It was realized that considerable time would be needed to deploy a new technology on such an extensive scale, and so the next generation IP effort was begun. The result of this effort was the specification of IP version 6. The format of IP version 6 is shown in this figure on your screen. The most important changes introduced in IPv6 are evident in the datagram format. IPv6 increases the size of the IP address from 32 to 128 bits. This ensures that the world will not run out of IP addresses. Now, every grain of sand on the planet can have an IP address. In addition to unicast and multicast addresses, IPv6 has introduced a new type of address called an anycast address, which allows a datagram to be delivered to any one of a group of hosts. This figure could be used, for example, to send an HTTP GET to the nearest of a number of mirror sites that contain a given document. A number of IPv4 fields have been dropped or made optional, providing a streamlining 40-byte header. The resulting 40-byte fixed-length header allows for faster processing of the IP datagram. A new encoding of options allows for more flexible options processing. IPv6 has an elusive definition of a flow. This allows labeling of packets belonging to a particular flow for which the sender requests special handling, such as a non-default quality of service or a real-time service. For example, audio and video transmission might likely be treated as a flow. On the other hand, the more traditional applications such as file transfer and email might not be treated as flows. It is possible that the traffic carried by a high priority user might also be treated as a flow. What is clear, however, is that the designers of IPv6 foresee the eventual need to be able to differentiate among flows, even if the exact meaning of a flow has not yet been defined. The IPv6 header also has an 8-bit traffic class field. This field can be used to give the priority to datagrams within a flow, or it can be used to give priority to datagrams from certain applications such as ICMP over datagrams from other applications. These following fields are defined in IPv6. Version. This 4-bit field identifies the IP version number. Not surprisingly, IPv6 carries a value of 6 in this field. Note, though, that putting a 4 in this field does not create a valid IPv4 datagram. If it did, life would be a lot simpler. We'll talk more about this when we get to the part regarding the transition of IPv4 to IPv6. Traffic class. This 8-bit field is similar in spirit to the TOS field we saw in IP version 4. Flow label. As we just discussed, this 20-bit field is used to identify a flow of datagrams. Payload length. This 16-bit value is treated as an unsigned integer given the number of bytes in the IPv6 datagram following the fixed-length 40-byte datagram header. Next header. This field identifies the protocol to which the contents, that is the data field, of this datagram will be delivered, for example to TCP or UDP. The field uses the same values as the protocol field in the IPv4 header. Hop limit. The contents of this field are decremented by 1 by each router that forwards the datagram. If the hop limit count reaches 0, the datagram is discarded. Source and destination addresses. Obviously, that's self-explanatory. Data. This is the payload portion of the IPv6 datagram. When the datagram reaches its destination, the payload will be removed from the IP datagram and passed on to the protocol specified in the next header field. This discussion identified the purpose of the fields that are included in the IPv6 datagram. Comparing the IPv6 datagram format in this figure with the IP version 4 datagram that we saw earlier, we notice that several fields appearing in the IPv4 datagram are no longer present in the IPv6 datagram. As far as fragmentation and reassembly, IPv6 does not allow for fragmentation or reassembly at intermediate routers. These operations can only be performed by the source and the destination. If an IPv6 datagram received by a router is too large to be forwarded over the outgoing link, the router simply drops the datagram and sends a packet too big ICMP error message back to the sender. The sender can then resend the data using a smaller IP datagram size. Fragmentation and reassembly is a time-consuming operation. Removing this functionality from the routers and placing it squarely in the end systems considerably speeds up IP forwarding within the network. Regarding a checksum, because the transport layer, link layer, and Ethernet protocols in the internet layers perform checksumming, the designers of IP probably felt that this functionality was sufficiently redundant in the network layer that it could be removed. Once again, fast processing of IP packets was a central concern. Recall from our discussion of IPv4 earlier that since the IPv4 header contains a time to live field, which is similar to that hop limit field in IPv6, the IPv4 header checksum needed to be recomputed at every router. As with fragmentation and reassembly, this too was a costly operation in IPv4. An option field is no longer part of standard IP header. However, it has not gone away. Instead, the options field is one of the possible next headers pointed to from within IPv6. That is, just as TCP or UDP protocol headers can be the next header within the IP packet, so too can an options field. The removal of the options field results in a fixed length 40-byte IP header. Recall that the ICMP protocol is used by IP nodes to report error conditions and provide limited information to an end system. A new version of ICMP has been defined for IP version 6. In addition to reorganizing the existing ICMP type and code definitions, ICMP version 6 also adds new types and codes required by the new IPv6 functionality. These include the packet too big type and the unrecognized IPv6 options error code. In addition, ICMP v6 includes the functionality of the Internet Group Management Protocol, which is used to manage a host joining and leaving of multicast groups, which was previously a separate protocol from ICMP in IP version 4. Well, we're about to start talking about the transitioning from IPv4 to IPv6, so let's just stop with this one right here and go over our notes and update our study guide. When you're ready, we will proceed.